All right, so let's pick up here. We're in the chapter on entropy, and we've covered a lot of material near the end of this chapter. One of the more important or significant, very applicable sections is this long worded section talking about the heat transfer and the work for internally reversible, so internally reversible, steady flow processes. So what are they talking about? Well, if you think about a system and you have inlet flow and outlet flow, 1 and state 2, if the system's operating in steady state, then the mass flow rate is the same through it. 1 is equal to 2. And in general, for this system, we have a rate of heat transfer, Q dot, coming in, and a rate of work transfer, W dot, across the boundary of the control volume. I won't put a CV subscript on there. And there's a very interesting result that if you have the work per unit mass, so we're using a lowercase w, if it's internally reversible, so it's for an internally reversible, what does that mean about internally reversible? What is sigma dot inside that control volume? 0, right? No, it's frictionless. Frictionless behavior, frictionless flow through it. And it's not just frictionless, there's no other sources of irreversibilities, but that's the main one, friction. It can be written as the minus the integral VdP minus any changes in the kinetic energy minus any changes in the potential energy. What are they talking about here? This equation looks startling. Before we derive it, let's try and understand it. What they're saying is this work per unit mass flow rate, if I had internally reversible, that would be the type of behavior that we're describing, is equal to minus the integral VdP minus changing. What looks wrong? Doesn't this look wrong? What should it look like? Well, I remember from a closed system that f dx is equal to the work, integral f dx, true? And that's equal to the integral pdv, the boundary work. So when I look at this, that looks just looks wrong, doesn't it? Is there a typo, Professor? Should this be the integral pdv? Nope, that's a surprising result. It's the integral v dp, just the opposite. Maybe that's why thermodynamics is sometimes hard for students. It's like, hold it, I just I invested a lot of time to learn something like this, and now all of a sudden something very much different comes along, and it confuses me as a student. Okay, but it's correct as written. Okay. What do you mean by the change in kinetic energy? Is this term the specific kinetic energy on the exit minus the specific kinetic energy on the inlet? Is that what we mean by the lowercase ke, the change in lowercase ke? Yeah. And so that minus sign is important, and this minus sign is important as well. Let's do this for a minute. If we just drop out this term, let me do this. That we can drop that term out, right? Let's say that there's no change in the pressure. Would this equation make sense? That we would have, if the kinetic energy change was negative, so the delta Ke is negative, then a negative would be a positive work out. That would make sense. Likewise, if the change in the potential energy is negative, then a negative made a positive work out. So by themselves, these terms make sense, and then the minus sign, you can think through it, and yeah, that makes sense. The hard term is this one right here, the VDP. Well, where did that come from? Well, let's do this. We're now going to derive it. We're going to use a couple pieces or tools, okay? The one tool that we're going to use is the relationship about entropy. The change in the entropy is equal to a small amount of heat transfer divided by the boundary temperature at which it occurs, and assuming it's internally reversible. So if we could rewrite this equation, we could say that del Q is equal to T ds. We've seen that a couple of times, right? When is that true? When it's internally reversible. That means that the entropy change is only due to a heat transfer, not because of irreversibilities. All right. Another thing that we're going to use that TDS is equal to DH minus VDP. Where did that come from? Where did this come from? The first piece came from the basic definition of entropy. The second piece is, I have a new property, entropy, and I can relate it to my other properties through property relations. And that's a property relation. Now we call it the TDS relation, or one of the two TDS relations. Okay. So now let's start the derivation to come up with this very unique equation. We'll start with the first law. And so what does the first law look like for this control volume right here? It looks like something like the rate at which heat is flowing into the system minus the rate at which it's flowing out. I'll put a CV on that work now. I'll just leave it off. The power at which the shaft work is crossing the control volume, and you're bringing in a mass flow rate with its inlet enthalpy, leaving with its exit enthalpy, bringing in with its inlet kinetic energy, exiting kinetic energy, inlet potential energy, exit potential energy. And if all of the sum of all those terms is not equal to 0, then there's going to be a rate of change of the energy inside the control volume. So we would write dE control volume dt. So how can the energy change? Well, if there's more flowing in than out. True? Do you like this equation? So now what we're going to do is we're going to say this is for steady flow. Okay, and I'm going to put a lowercase q is equal to q dot divided by m dot. Is that not true? Just like lowercase w was w dot divided by m dot, it's the specific heat transfer and the specific work transfers. It's the how much per unit mass is flowing through the system. So what we'll do is we can do this. We'll write it as del W, or just do this one, lowercase w is equal to lowercase q minus the change in the enthalpy minus the change in the kinetic energy minus the change in the potential energy. Did I write it okay? You follow that? Why did I have to put a minus sign in front of that changes of kinetic and potential energy and as well as enthalpy? Because I needed to switch the order, right? I needed to switch the order, get the H2 minus the H1. That's really the delta H. Okay, so that look good? Okay. So at this point we could even think about a really small amount of heat transfer, a really small amount. Maybe I should do that in another step. I think I have room. A very small amount of work transfer, a very small amount of heat transfer minus DH, okay? minus the change in the kinetic energy minus the change in the potential energy. I could have stayed with a finite change and a finite amount, or just move it to very small, infinitesimally small amount. All right, well at this point, what we'll do is we'll say we're going to restrict this now to internally reversible processes, so we can replace that by TdS. And what about the dH? Well, I look over here to this equation, and I see that dH is equal to TdS plus VdP. Did I write that equation right? Yeah, I think that's right. So what we have here is we'll replace the dH by, we'll put the minus sign, got to watch out our minus signs, TdS plus VdP minus the change in the kinetic energy minus the change in the potential energy. Okay. So which two terms cancel? Those two terms cancel. And we're left with basically the form we wanted to get to. The small amount of work transfer per unit amount of mass transfer is equal to minus VdP minus the change in the kinetic energy minus the small change in potential energy. If I want to move it back to a finite change, just go ahead and do the integration. And so this would be the small w. This is restricted to be int rev. Sometimes it's emphasized with that subscript on that w, is equal to the minus the integral VdP, that surprising term that looked wrong, but there it is, minus the change in the kinetic energy minus the change in the potential energy, and that's usually the symbol the mathematicians put, QED, right? Some Latin for what we set out to demonstrate has now been demonstrated. So this is the equation. And it's somewhat useful. Let's now go ahead and talk about applying that equation to two things. One is a pump and one is a compressor. So here's a symbol for a pump. The fluid comes in at state 1, goes out at state 2. It's typical that for a pump, what is the Q dot for a pump? 0. And we're going to draw W dot coming out of the pump, but we know that that term is negative. A pump is not a work-producing device, it's a work-consuming device, but we're just going to work with it as W dot positive out, hence it'll be a negative into the pump. The next one is a compressor. Maybe we change the symbol on the compressor. Maybe it comes in with this. It really doesn't. You could draw a box for a pump and a box for a compressor. That's just as good. And then it goes out at state 2. And the same thing for a compressor. Typically, it's not a lot of heat transfer, so we neglect the amount of heat transfer. And then we have not W dot out of the compressor, but it's into, so we know that this is going to be negative. All right. What is ingested in what type of fluid is taken that a pump uses, that goes through a pump? What type of fluid goes through a pump? What type of fluid goes through a compressor, and how are they different? What goes through a pump? Liquids. And what goes through a compressor? Gases, vapors. So gases, vapors. All right. One of the big conclusions about properties of these two substances, just kind of put it up here. Talk about the specific volume of a liquid and compare that to the specific volume of a gas. The specific volume, the typical specific volume of a liquid that goes through a pump, compare that to the specific volume of a gas that goes through a compressor. Which is greater? This one, or that one? Which is correct? Answer A, answer B, or answer C? Is the specific volume of liquid greater than the vapor or the gas? Is it equal, roughly equal, or is it the opposite? C, is it the specific volume of liquid much less than the specific volume of a gas? I'm going to pause and walk around and see what you get for that. It's really important, that point. It's almost too trivial, isn't it? And so did I mention I always use my hands when I'm trying to understand or explain specific volume? And the volume encompassed by my two hands like around a ball. And if it's a small specific volume, a slow value of specific volume, I don't need very many cubic inches for a pound, or I don't need very many cubic meters for a kilogram. But if it's large volume, then I need more space for the same amount of mass. So when I think of liquids, oh, they're compact, they're dense. It's a very small value of the specific volume compared to the gas, which needs more room. So which way does it go? Goes that way, doesn't it? That's one thing to remember. Keep that straight in your mind. Okay, let's make a list of kind of properties. Oh, pressure is very important. Inlet, pressure on the outlet. What can we deduce about the pressure outlet compared to the pressure inlet? Isn't the pressure outlet from a pump greater than inlet pressure? Does that statement make sense? Yeah, that's the purpose of the pump. Boost the pressure, right? Let's talk about temperature. Well, let's come back and talk about temperature. Let's talk about another favorite property, specific volume. Let's talk about enthalpy. Let's talk about entropy. I mean, I could have put in U, maybe that's fine, put in U. Keep it in the order. Isn't this the order that we have a lot of properties in our textbook? Isn't it P, T, V, U, H, S? Okay. I'm going to delay the discussion on temperature for a second. Talk to me about how does the specific volume on the exit compare to the specific volume on the inlet for liquid going through a pump? Is the best answer A, B, or C? Which one is the best answer? You got to think. Now, if I ask you questions, please think. Which one is it? I'll walk around and see how other people answer. What does this mind? And critique it, right? So somebody, I forget who, somebody up here wrote, incompressible. What does that mean? Are liquids incompressible? You bet they are. That's a great approximation. I didn't say precisely incompressible, it's a great approximation. So if it's incompressible, what about the specific volume on the outlet compared to the specific volume on the inlet? They're the same. That's a good assumption, good approximation. Now, we can talk about these. How about the exit enthalpy compared to the inlet enthalpy? Greater, equal, less? What do you think? Greater. And what was the logic behind the greater? You boosted the pressure, you put in energy, that's the purpose of the pump. It put in flow, it increased the flow energy of the liquid going through it. And that's realized by an increase in the P. And the PV plus U gives a H, it's higher. Okay. What about entropy? S1 versus S2. S1 greater, equal, less? If it was a bad pump, not an optimal pump, then it would be greater. If it was a great pump, a super great pump, good fit pump, highly efficient pump, what? Equal. It's if dream pump, like it can't be realized, it would be less. I mean, it would break the second law of thermodynamics. Typically, we have no heat transfer for our pumps. It's not a heat transfer device. So this is the way it typically goes for analysis. Okay, this is going to be greater. Okay, now let's think about it. Let's tackle temperature for a minute. What do you think? Pump. Liquid water flowing through the pump. You may or may not have any experience with it. But what's the purpose of the pump? To boost the pressure? Yes or no? Or to boost the temperature? There's no real advantage to boosting the temperature. It's to boost the pressure. So this is essentially the same. The temperature is essentially the same. And internal energy of a liquid is primarily a function of temperature. And so this is essentially the same as well. This is I like to avoid talking about U's because it's really the flow energy, the enthalpy, that's most important for the first law in the analysis of the pump. Let's do the same thing for the compressor. Make our list of properties: pressure, temperature, specific volume, internal energy, enthalpy, entropy. Put it at state 1, state 1, state 1, state 1, state 1. What's state 1? All on the inlet. Put the same list: pressure on the exit, temperature on the exit, specific volume of the exit, internal energy on the exit, enthalpy the exit, entropy exit. And just trying to say, what is the relationship for a compressor where you're having a gas or a vapor going through it? What about the pressure? Is the pressure outlet, less than, equal to, greater than the pressure inlet? Which way does it go? It's a compressor. The purpose is to increase the pressure. Let's skip temperature for a second. Let's talk about specific volume, because this is kind of a key. The specific volume is key. What happens to the specific volume of a vapor when I put it through the compressor? Does it come out larger or smaller? You're compressing it. And so the specific volume on the outlet, is that correct or incorrect? It's correct. Yeah, good. Now let's skip internal energy and let's jump to enthalpy. What about the enthalpy on the exit compared to the inlet? Greater. True? If I look at the first law, that W dot, I know this is a negative, so I'm going to put is equal to minus, or put a negative right there. M dot times the H 2 minus H1 there. I think I wrote that correctly with the minus sign. So a minus on a minus makes it a positive work, which is really coming into the system, and it's going to increase the enthalpy above the inlet enthalpy. H2 is greater than H1. What about entropy? Well, if it's not a very good compressor, there's a lot of friction, irreversibilities, but let's say it's the best compressor the best engineer could ever design and implement and build. Frictionless compressor. Would it be equal? That's the best we can do. So we're going to analyze it as the best compressor, right? This would be the best pump. This would be the best compressor. Now maybe we take a look back at the temperatures. From experience, intuition or just experience, what about that temperature of the gas? It's going to go up, way up. Why? I have a device that just boosts the pressure of the flowing fluid. One device has negligible temperature increase. One device has significant temperature increase. Why? Pardon? Yeah, because it is compressible, and as you compress it, there's work associated with that compression, and that energy is going into the fluid, and it's going to be realized not only by an increase in pressure, but an increase in temperature. Temperature and pressure and specific volume of gases and vapors are not independent. You could think of them being linked, like you said, to the ideal gas equation. So maybe you take PV is equal to RT. The pressure went up, the specific volume went down, but your temperature is going to go up too. So this is up T1. What about internal energy? Primarily linked. I know it's a function of, if it's a true ideal gas, it's only a function of temperature. If it's a vapor, it can be a function of temperature and pressure, but it's going to go up. True? Okay. Now, somebody says the kinetic energy, talk to me a little bit about the change in the kinetic energy and the change in the potential energy for the fluid going through the pump. Most pumps, what would we say? Negligible. The negligible change in kinetic, negligible change in potential. How about for a compressor? Change in kinetic energy, compare that with the change in potential energy. Are you boosting its speed a lot? Are you boosting its elevation a lot? No. A small control volume focused around the pump and around the compressor, most analysis would say, nope, negligible changes in kinetic and potential energy. So now we go and we say, the equation that we just had, the W min, the minimum work, meaning it's internally reversible flow through that device. Why do I put a lowercase w? Because it's the minimum work per unit mass of the fluid flowing through. It's the minimum kilojoules per kilogram of the mass flowing through is equal to the negative, the integral V dP, and we had negative change in kinetic energy, but we just talked about why that's equal to 0, and negative change in potential energy, we just talked about that's 0. So really, this is the term that explains it. And that equation applies for both the pump and the compressor, does it not? Let's do this. We like property diagrams. Do you like property diagrams? Sorry, I have to scroll down. What would be a good property diagram if I want to investigate this term, this PV term, this integral PV term? What would be a good, let's do a PV diagram. Have you seen a PV diagram in this class? Sure. Let's do one PV diagram. Well, we can put them both on the same PV diagram or do them independently. Okay, one is still for the pump over here, one is for the compressor. Let's somehow locate the same inlet pressure. So the inlet pressure is right here on both of these scales. It's low, isn't that P1? Doesn't P1 low make sense? What about the inlet specific volume to the pump? Compare that to the inlet specific volume of the gas compressor. Which one? Well, one is going to have a low inlet and one a pretty large inlet. Isn't the gas needing more volume per kilogram than the liquid? Sure. So here is state 1 on the one diagram. Here's state 1 on the other diagram. True? Now, where is state 2 on the pump PV diagram? The exit pressure and specific volume coming out of the pump. And where is state 2 on the PV diagram for the compressor? I'm going to pause, walk around, and you just use the same logic that I did. I'm thinking what pressure and specific volume. All right, for comparison purposes, we'll take them both up to the same exit pressure. So we're trying to make a pretty good comparison. The easier one is for the pump, isn't it? Because does the specific volume change? No. So what happens? There's state 2. And what's the process look like on a PV diagram? Straight up to state 2. Now, on the gas for the compressor, the volume is going to go down. but it probably is not going to get down into the range of a liquid. It's probably going to go down, but it's not going to get down there, so it's going to be somewhere maybe out in this vicinity. We're going to get up to the same pressure, but we're not going to get it as squeezed down to be as in the liquid state. It's still in a gas, still in a vapor coming out. We can have a gas compressor or vapor compressors. And so it would look something like this. It would have probably a little belly to it. There would be it's not a perfectly straight line, but it's a little belly to it. Okay? True? All right. Now, what this equation says is the integral of VdP, the minus the integral of VdP is that work. Don't worry too much about the negative sign. We know it's not positive out, it's negative in, you know. But it's what is this VdP from calculus? They probably showed you early on. If I'm trying to compute this integral, right, here's my f as a function of x. I'm going from a to b, and my function goes like this. Then what is the integral f dx from a to b? Isn't it visually the area under the curve? True? But we're looking at this integral, and we're saying the integral v dp, but where's the change? I'm not on the x-axis, it's on my y-axis. So to do this correct, what I need to do is I need to flip it. Nothing says we have to put P on the quote-unquote y-axis. Let's put P on the x-axis. And let's put V on the y-axis. Can you do that for both of these? Can you transform them and give me a VP plot for the same processes? If this is the first time you do it, you really go slow so you avoid a mistake. So we're going to have a low value of the specific volume, just like we had the low value specific volume V1. And then we had a low pressure, so that's P1, and then the high pressure P2, and that's the process from state 1 to state 2. Okay, let's now do it also. So we're going to have a high value of specific volume 1, but we really don't want to show V2 for the gas to be nearly as low because we're trying to compare the plots on the right with the plots on the left. So let's stop V2 right here, right? We don't want to take it all the way down. And but we do want the pressure P1 and P2 to be roughly the same as the two plots. And so we're going to start here and we're going to go to there. And it'll have just a little curvature to it. It could be nearly a straight line. But would that be 1 to 2? Now if somebody said, show me a visual image of VdP, wouldn't it be this? And wouldn't it be this? And guess what? That size of that area signifies. It signifies the magnitude of the integral VdP. So which one is larger? This is much larger. Much larger area. Hence, the work per unit kilogram for the same pressure change for the compressor is much greater than the work per kilogram for the pump for the same pressure change. Same pressure change. All right. If you go back and say, well, I don't like to always flip it, I like to see it on a PV diagram, well, guess what? It's just this area. But that's not area under the curve. It's the area to the left, isn't it? And likewise, this area. That's the same area. So a lot of times they won't change the order of the axes. They'll put it on a PV diagram and they'll shade the area to the left of the curve. Why do they put a solid line between states 1 and 2? And the solid line between states 1 and 2? because it's internally reversible process. If there are irreversibilities, guess what? I'd have to put a dashed line, and then I cannot interpret the area to the side of that curve as some minimum work. This only works if you have the internally reversible assumption. You can also get Bernoulli's equation from the equation we just had. Well, what was the equation we just had? We had the work internally reversible equal to the minus the integral VdP minus the change in the kinetic energy minus the change in the potential energy. Who remembers Bernoulli's equation from Physics 1? Or another class? Do you remember Bernoulli's equation for fluid flow? What it said was, we have a little pack of fluid and it's flowing through the system. There's the little pack of fluid later. We're not going to do transient. This is steady state. So guess what? That path line is equal to a streamline of the fluid. So this is a streamline of the fluid. Okay. And this type of fluid that we're simplifying assumptions, we'll say it's frictionless fluid. In other words, inviscid. Inviscid meaning no viscosity, negligible viscosity, fluid flow. And to make it look like Thermo 1, we won't just look at a line, even though in physics and in fluids they just look at a fluid packet along that streamline. They'll put a little area around it, and now that's not a streamline, but that's a, guess what? It's not a line, it's a tube, stream tube. Tube, okay, TUB. So what we have is we have the inlet to the tube, state 1. We have the outlet to this tube, state 2. Hey, that looks like a control volume. Sure is. Is there any other boundary at which flow of mass is cutting in or out of that stream tube? No, just on the inlet and only on the outlet. And then if you apply this first law, with the assumption it's internally reversible, bringing in the entropy concepts and reversibility, you get this equation. There's a number of assumptions in this equation in the derivation, right? So tell me about the change in the internal energy of the flowing fluid. Negligible. Tell me a little bit about the fluid that Bernoulli's equation is applied to. Specific volumes of constant. What's that mean? It's a incompressible substance, incompressible. Bernoulli's equation. How many people really have never heard of Bernoulli's equation? Put your hand up. 1, 2, okay. 3, did you throw away your physics textbook? Your Physics 1 textbook. Look. Just go look at it. It's in there. Okay? And it's a fundamental equation that mechanical engineers should dominate. You should have already seen it, and this is another chance to see it, but when you get into fluids, you should really see it, okay? And you should use it a lot. And I can pretty much guarantee it's on the EIT exam, meaning this is sort of essential knowledge for any mechanical engineer who graduated from any ABET accredited program. There should be nobody in the world that's claiming to be a mechanical engineer doesn't know Bernoulli's equation, period. That's how strongly it's at, right? Okay, so I'm encouraging you to go back and review and then tie it in with what we got. We're doing it. It's covered in our thermo textbook, Bernoulli's equation. It falls out of the energy equation. So we have that volume, specific volumes of constant, meaning it's incompressible. It's a steady flow. It's along a streamline. Here we'd say stream tube, okay. And did I already cover it's inviscid? No friction. And what do we pick up? There's about 4 or 5 assumptions. And if it's incompressible, what happens to the specific volume on that integral? I can take it outside. So we're going to get that the minus the change in the pressure, minus the change in the kinetic energy, minus the change of potential energy. If the stream tube has no work cutting across it, W dot CV 0, no work going across it, That's 0. Okay, so now we can write it like this. We can write it as negative 1 over rho, pressure 2 minus pressure 1, minus the kinetic energy is 1/2 V2 squared minus 1/2 V1 squared, minus Z2 minus Z1. What do you mean by Z? The elevation, right? We used Z before. So now I can multiply through by rho and organize, and let's put all the P1 plus, let's do it over here, plus 1/2 rho V1 squared plus rho GZ1 is equal to P2 on exit plus 1/2 rho V2 squared plus rho GZ2. I'm going to pause. Did I do the algebra right? Did I mess up a minus sign anywhere? Give me a thumbs up if you like it, but only after your brain has processed it, right? Does it look okay?
To subscript for your second Z. Pretty much it.
I'm missing a second subscript for what?
Oh, no, it's right there.
This is V2 right there, yeah. And so basically you could have cut V2 here, you could have cut V2 there, you could cut V2 there. What you find is that something's a constant, something's conserved no matter how long that stream tube is, as long as it's the same streamline that it's covering, same packs of fluid coming in and out. And so what they're saying is it's a Bernoulli's equation is a conservation mechanical energy equation for flowing fluid packs. And you have the pressure, and you have the 1/2 rho V squared and the rho GZ. Each of these have units of pressure. You can interpret it as energy per unit volume. So something's flowing along, energy per unit volume. If you want, you could put the pressure and you bring over the density, and you have the 1/2 V squared plus GZ, and now that's equal to a constant, inlet equal to the outlet. And now this is not energy per unit volume, but this is energy per unit mass. And that's a little more familiar coming out of Thermo 1. It's 1/2 V squared or GZ. Those are both the kinetic and the potential energy per unit mass of the pack of fluid. And then there's another form, but one form of Bernoulli's is good enough. Okay? How many people dust off a few cobwebs? You saw it now. You're a little more familiar. Bernoulli's equation. What's a classic example of it? Let's say I have a tank of water, and I have a hole in the bottom of the tank of water, and the fluid level is up this high, and I want an estimate of how fast it's going to gush out of that hole in the bottom of the tank. Anybody remember doing this one? What is the exit speed V2? How do I calculate it? Well, you introduce a streamline that says, you know what? Every little fluid pack that starts at the top, if I wait long enough, is eventually going to go out that hole. So I'll start it at the streamline at this point, exit that point. Inlet 1, exit 2. And then I say, okay, the pressure at 1 plus 1/2 rho V1 squared plus rho GZ1 is equal to the pressure at 2 plus 1/2 rho V2 squared plus rho GZ2. And what am I really interested in? I'm really interested in V2. I want to calculate the exit speed coming out the hole, the bottom of the tank. Okay, well, tell me a little bit about the pressure at 1. If it's air above the tank, water tank, what's the pressure at 1? Atmospheric pressure. What's the pressure at 2, the air under the tank? What's the pressure of the air under the tank? Atmospheric pressure. What's the pressure of the fluid issuing out of the hole at the bottom of the tank. It's atmospheric pressure. So guess what? These two pressures are the same. They cancel. I have a large diameter tank. It's slowly draining. What's the velocity of the fluid particle at 1? Negligible. So what we find is that the height difference, this height of the water level of the tank, okay, that's just Z1 minus Z2, isn't it? So what you have is you have 1/2 rho V exit squared equal to rho G Z1 minus Z2. Cancel the rows. And we're going to get that the velocity exit is equal to the square root of 2GH. You do the same thing now in fluid mechanics. All right. Well, you'll do this a lot more than that in fluid mechanics, but at least that's the same thing in thermo. So there you go, Bernoulli's equation linked into our energy equation. 4, internally reversible process, number of assumptions, steady state, and there's no work. So that work term goes away. Let's solve this problem. We have saturated liquid water. At 100 kilopascal, it enters a pump and exits at 3,000 kilopascal. The pump acts isentropically, so it's reversible, no heat transfer, so it's isentropic flow through the pump. Determine the work required to pump the water. Okay, what symbol would we like to use for answer part A? The work required to pump the water. Okay, W dot, but then I'm going to need to know M dot. But if I don't know M dot, I'll just divide W dot by M dot, and that's a good power per unit mass flow rate or energy per unit mass of the water flowing through. A lot of times we just say that's lowercase w. Okay, that's good. So how are we going to calculate lowercase w? Well, is it internally reversible? Sure. And we just did that where we had the int rev is equal to minus the integral VdP minus the change in kinetic energy and the change in potential energy. Well, those are negligible for a pump. It's the integral VdP. Hey, V is not changing. It's nearly incompressible. It's a liquid, water, liquid going through. It's just going to be minus V times P2 minus P1. True or false? And now you say W int rev, you'll see that, oh, that's where I'm going to have a negative sign. It's not work out of the pump, it's work into the pump. And so let's just run some numbers. What would be the specific volume? You can look it up, and I'm glad you're looking it up in the table, but how many people have looked up enough times the specific volume of liquid water to get a good number for it? Okay, how much, what is the density of liquid water? 1,000 kilograms per cubic meter. How much, if I have a liter, 1 liter water bottle, nobody's got one on their desk around here, right? And I pick it up, it's full of water. I can get a good sense of how much mass that is. 1 liter, how many kilograms liquid water? 1 kilogram, right? 1 kilo. If you have a half a liter water bottle, the little plastic half, that's half a kilo. Don't leave this class without that type of basic knowledge, okay? So it's going to be 0.001 meters cubed per kilogram. 0.001 meter cube is a liter. That's a specific volume. It's 1 liter, 1 kilogram. Or the volume, if I have 1 kilogram of liquid water, I need a liter to occupy its space. That's how much space it occupies. And then we had the pressure change. Well, it went up to 3,000. It started at 100 kilopascal. I'm going to have to do some unit conversions here. True? What's meter cubed times a kilopascal? Done it enough to know that's a kilojoule? Precisely is. And that'll give me the right units, won't it? So if you have a calculator, can you please, well, you don't even need a calculator. What's 3,000 minus 100? 2,900. Multiply by 0.001. 2.9. Hey, I'm shaking. I have tremors or something because I made some math calculations without a calculator. Maybe we should have exams without calculators. No? But you would get better at rounding things off. Right? Okay. And a lot of engineering calculations can be made that way. You know it. I mean, do you want the automobile that you drive to be designed such that the load calc at which it brakes, you know, they fine-tuned it so much that if you get close to it, it breaks? And no, you want a large factor of safety. So anyway, okay, so this is how many kilojoules per kilogram. If I rounded that number off, round it off to one significant digit for me. 3. All right, try and remember that number. Okay, but what we're going to do is we're going to now forget this next part where we throw in some isentropic efficiency. Do that later. What is the state of the water that leaves the pump? Is it superheated vapor, saturated liquid, subcooled liquid, two-phase liquid vapor? What is it? Compressed liquid. It's compressed liquid. It's liquid, right? That's what comes out of the pump. So think about plotting this on a temperature entropy diagram. Here is temperature. Here is entropy for water, drawn to scale using a NIST program, RefProp. And where is our initial state on this plot? Well, go back and reread the problem. It's saturated liquid at 100 kilopascal. Can you find that state, initial state on this plot, state 1? Saturated liquid, 100 kilopascal. How about I pause and you find it? You know what I mean? Redo. But I really want you to pick this up because you got to own it, right? If you learn this, it'll just help you a lot in Thermo 2. All right. So we said that it came in as saturated liquid at 100 kilopascal. 100 kilopascal, a lot of people are going, okay, right there, that's 0.1 megapascal. It's somewhere along this line. And where is it along that line? Right there. It's around 100 degrees C. And it's at this value of entropy. So there's state 1, and there's S1, and there's T1. Now, somebody says, I put it through. It's going to end up on the line of 3,000 kilopascal, which is 3 megapascal. It's going to end up somewhere along this line. Where does that line go after it hits that spot? It goes like that, doesn't it? Okay. So where is it going to go? I've seen some answers put it out here. Some of them put it there. Okay. How about answer A, answer B, or answer C, somewhere else? Let's narrow it down. Could it be A or B? A is not right because that's saturated vapor. Well, it's at the right pressure, but can you tell me a little bit about the entropy value at A compared to the entropy value at the inlet? What type of pump are we running here? A pretty lousy pump or a pretty good pump? A really, really good pump, right? So what about the exit entropy? What about S2? You can't be way out here. This is not S2. No way. How about right here? Is that S2? No. Where is state 2? Straight up on the line of higher pressure. Well, is that some person put it out here? Is that where it's at? No, because that line of 3 megapascal kicks way down right in here. Guess what you have to do to see state 2? Get a magnifying glass and zoom in. There you go. There's your magnifying glass zoomed in. And what is the red line? The dome. What is the intersection right here? State 1. What's the pressure? 100 kilopascal. We're going to go straight up till we hit the line of 3 megapascal. There it is. Right there is state 2. You have to zoom in. There's no other way. Let's talk about the temperature change. It wasn't precisely 100 at 0.1 megapascal. It's 99.8, right? Or 6, 99.6. What is the temperature after coming out of the pump? 99.7 or something. It's not much higher. Is it a little higher? Yes, I grant you it's higher by a little bit. Okay? So this point right here always trips students up. And what will happen is we'll whip out and we'll say, well, let's sketch this on a temperature entropy diagram. Here's the dome, here's state 1, here's state 2. And we'll exaggerate how far 2 is above state 1. It's isentropic. Whoops, I got to get it on top, the straight line, right? Okay, I messed that up. But you get that it's the same S, but they exaggerate the temperature difference. So just like we talked about a couple minutes ago, the pump's purpose is not to boost the temperature. There's a little boost in temperature, but it's very, very, very small. It's negligible for most calculations. Okay? All right. Same pressure, same substance. It's water. Everything's the same, but instead of putting it into a pump, I changed the word to compressor. And instead of putting in saturated liquid, what do we put in? Saturated vapor. Do the same problem and tell me, what is that work required to compress the water, to boost the pressure of the water from 1,000 kilopascal to 3,000 kilopascal? How would you calculate it? Let me try and sketch some stuff out. Here's state 1, state 2, inlet 1, exit 2, and the W dot of the compressor going, it'll be negative. So lowercase w compressor. I know we can put the minus the integral VdP. Can I change that specific volume, bring it outside the integral? No. No. And so this approach is kind of what I'd say a dead end. Even though we just learned it and we applied it to the pump, it was really slick. We was like, oh, that's VdP. But what we have to do is we have to go back and we have to say pressure inlet, temperature inlet, list all the properties of interest, V inlet, U inlet, H inlet, S inlet. How about the pressure outlet, temperature outlet, specific volume outlet, enthalpy outlet, entropy outlet, okay? We can get the value for the pressures. It's 100 kPa and then 3 MPa, true. And we can, because it's saturated vapor, did the temperature change? No, it's roughly 100 degrees C. It's about, well, let's just call it close enough to 100 degrees C. Okay, specific volume, that's V sub G at that pressure, 100 kilopascal. How about H? H of G, I can get that out of the table. How about S? S of G, isn't it? Is it all saturated vapor? Okay, let's go over here. Either from the first law analysis for the control volume around the compressor or the second law analysis for the control volume around the compressor. It's Q dot's equal to 0, no heat transfer. It's isentropic compression, that's sigma dot equal to 0, so that both the sigma dot 0, Q dot 0, it's adiabatic, it's reversible, hence it's isentropic. What do we know in this list over here from the second law? S2. S2. Because from the second law, S2 is equal to S1. Now I have two independent intensive properties from the state principle. I can fix the other states. I can find the other states, or the values for that state. I can find H2. I can find V2. I can find T2. It may be useful to maybe sketch this on a temperature entropy diagram. Before we run off and make some calcs, where is state 1 now for the new problem on this temperature entropy diagram?
Same pressure line, but on the right side of the room.
Way over here, isn't it? Now I'm going to put it through a compressor. I've got to get up to this line of constant pressure. How am I going to do it? Well, maybe I'll go that way. No. S2 has to equal to S1. Straight up. Guess what temperature you're going to be at? Pretty high. Even over 400 degrees C. Same pressure change. Same substance. It's water. It's just instead of saturated liquid, I had saturated vapor. Instead of putting it through the pump, I put it through a compressor. Isn't this incredible? Look how much change it is in the temperature. So what we do now is we can go back and make our calculations. And we'll have to go to our two-phase table because it's going to be superheated vapor, isn't it? And in our two-phase table, let me see if I have it here. Oh, I even blew it up even more. So 0.1, I want to go out to 3. And so you can tell it is hot. It is going to be high pressure, high temperature. So we find our 3 megapascal pressure block in our superheated steam table. We found that the S of G for state 1 comes in at around 7.3594. Hence, we know we're in this temperature range. We want to get this enthalpy. We do some linear interpolation. The enthalpy is 3556.7 and the temperature's 544.5. 545. Jump back here. Does it look like it's around 545? Close enough. That's a big temperature change. Went from about 100 to 545 degrees C temperature change. And the enthalpy is very high as well, 3,556. So what we do is we go back and answer the question. We find that the work per unit mass, the specific work, is just going to be the exit enthalpy minus the inlet enthalpy. Put the minus sign on it because it's a large negative number. And we calculate for this problem, it's around negative 881 kilojoules per kilogram. That's when you take in vapor. What was it as a reminder? If you took in liquid, okay, I have $3 on me. Anybody that has $881 on you, I'd like to play a game. You give me the 881, I'll give you the 3. What do you think of that exchange? Is this a small difference or a huge difference? This is a significant difference. This is why you have pumps to boost pressure, and you try to avoid, if at all possible, compressors to boost the pressure. It's a lot easier to cool it, condense it, put it through a pump, boost the pressure, then add heat to boil it again. It's 300 times, roughly, larger work. All right. I had more problems that I wanted to answer, but I have 2 problems that I'm ready to talk about today, and I have a page handout for you. So let me hand this out. So go ahead and just solve one of the 2 problems. Solve either this one. I got to get rid of this. Right here, where you have argon and a piston cylinder assembly. Or the next problem where you have refrigerant 134A entering a compressor. Okay? And I'm going to go ahead and stop and let you guys solve it and turn it in.